So this is TPS 2500S model for measuring thermal conductivity and thermal diffusivity for your samples. To turn on the machine, first you have to plug in the power cable. And then there's a switch at the back, which is the main switch. You have to turn it on. And there's a power switch here as well. So you should hear a beep sound. It means the system is powering up. And you will see some readings on the meters. Just don't worry about about the numbers, but you should see the green light and you should see these fluctuating numbers. So the next thing is you have to choose a sensor from the sensor inventory. The choice of sensor depends on what kind of samples you have, what are the dimensions of the sample. Then you have to make your sensor choice based on those dimensions. So we have different types of sensors with different sensor radius, and again the choice depends on your sample and the sensor dimensions, sample dimensions. All the numbers for the sensors, they are given here, so you can read. So this is a 5465 sensor. I think that's the smallest one we have. To measure the thermal conductivity, ideally you should have two identical samples with the same geometry and the same material composition. But in our case, we have one rounded sample, and the other one we have it in a rectangular form. You can also do one-sided experiments as well, but two-sided experiments are more easier and more accurate. But again, you will need two identical samples. So for this one, we will use these two samples. They are not identical, but we will try to see if we can get good results with somewhat dissimilar samples. So all of the sensors, they have this protective cover. So make sure whenever you are not using the sensor, you have to put the sensor in this protective cover so you don't get any wrinkles on the sensor, which is very sensitive. The next step is we have to plug in the sensor. So remove the protective cover, and to plug it in, you have to be very careful. So there's a red dot here on the sensor. You have to make sure that this red dot aligns with a red dot here on the machine. The reason is we have very sensitive copper pins inside, and you don't want to damage these pins. So make sure you align the red dots, and you don't need to apply a lot of force. Just a gentle push, and if you feel any resistance, you can try again. See, it should go in very easily, and you will hear a slight click sound. So sensor is in. So the next thing is we have a sample holder. Here we will put our sample. So we will remove the protective cover. So one sample will sit on the bottom face of the sample holder. Then you will take your sensor, while installing the sensor, you have to make sure that this black line is parallel to the steel strip, so that you make sure that it's exactly parallel or somewhat parallel to the sample holder. Gently so we have tried to concentric the sensor with the sample, and now we are putting another sample on top of it. And after that, you have to tighten this screw, but you don't want to damage your sample because this is a very pointy end for the holder. For that purpose, you will need to have some sort of copper strip. So you can place a copper strip between the sample and your holding screw. It also lets you to apply the uniform force on the face of the sample. So you can now tighten it up. And just make sure that the sample doesn't move if you apply slight force on it. After that, you just have to put back your insulation cover. This is just to avoid any radiation effect on the readings. And one important thing is to use the earth wire so that we don't get any electrical shocks or anything during the experiment. And we will just put the insulation cover on top. So now our sample and sensor are in place and we are good to start the measurements. So after setting up your sensor and sample, you have to run the hard disk thermal analyzer on the desktop, which looks like this. Double click on it. It will take some time for this to load up. So on this screen, you have different modules available with this equipment. You have bulk analysis, stack analysis, thermal resistance type 3 analysis, and several other options here. But to keep it simple for the demonstration, we are just going to use bulk type 1 and isotropic module. So this just makes an assumption that the material you are using has isotropic properties. And you just have to double click on bulk. To make sure your system is connected to your computer, there should be a green tick here. And if you don't see the green tick, it means there is no communication between TPS and your computer. So try unplugging your USB cable, try to reset, turn off and turn on again, and you should see a green tick here to confirm that you have an established connection. So on this settings window, you have a couple of options you can choose. So the first thing is the identity. So identity could be your material name or anything. You want it to be notes if you want to make any notes regarding your measurement. For us, we are just doing a test. The next thing is available probing depth. So available probing depth is the shortest distance between your sensor edge and the closest boundary to your sample. In our case, it is 7 millimeters, but you can refer to the notes for additional information regarding how do you calculate this probing depth. The next option is you have to select a sensor. So as we showed you before, the sensor we are using is 5465. So you have to select this from this drop-down list. Insulation is a Kapton insulation. Cable or holder, we are using a gray cable. So all of these settings are kind of default. You just have to select what kind of sensor you are using, which is 5465 in our case. The next thing is the sample temperature. This is actually, you can measure the sample temperature or you can just use the room temperature. For our case, this is 21.8. We have this sensor here which is out of batteries. This also shows you what's room temperature, current room temperature. The next thing is the two important things are the parameter wizard, which is the measurement time, and the heating power. The selection of these parameters you have to do iteratively. You can also refer to the manual what kind of ranges you should start with. You always have to start from the smallest numbers because you don't want to overheat your sample. So this is very critical. Always start with the smallest numbers. For the smallest numbers, I can show you the measurement time we can use is 1 second. Heating power, heating power, you can start from 1 milliwatts or 10 milliwatts or 100 milliwatts. Again, to get the rough estimate, you can refer to the manual, what kind of ranges you should start with, like for polymers, for metals, non-metals. You can get the rough idea from the manual. So once you select your parameters, then you have to click here on the start. Once you click on start, it will do some preliminary checks. It will measure some resistance value, which we already tuned for our device, so you don't have to make any changes here. Wait for this to go 100%, and it will show you what are your parameters once more. And for ignore the resistance value, just press OK. And once you press OK, your system or TPS will start measuring the thermal conductivity. Once it's measuring the thermal conductivity, you will see some values fluctuating here. This is just TPS trying to balance the Wheatstone bridge that this system uses as a principle. So it will adjust the values of voltages to balance the resistances across the Wheatstone bridge. You just have to wait. On the screen, you will see this dialog box where it says balancing the bridge. You don't have to do anything, but it is just to show you the progress. Once it's balanced, the calculation will stop. So it says within acceptance region, verifying stability. So on this bar, you can see all the progress. So we will let this calculation complete. So once your calculation is completed, you will see a graph like this. For the transient graph, you should see a very rapid temperature rise, then the temperature will stabilize. So this is a good graph. In the drift, you should see a uniform distribution of the measurement points. If you don't, then you can exclude some of the points by moving these yellow bars. So ideally, we want to exclude the points where we see there is some deviation in the measures, like it's not a straight line. So I will just move this yellow bar over here to exclude some of these points, and at the end of the reading, you can exclude some of the points. Once you do that, you go and drift again. So yeah, we should see some uniform pattern of the measurement points, and then you go and calculate it. Here you have to click on calculate. Here it's a start and end point, which we selected manually using the yellow bars. If you know the specific heat of the sample, you can input here. That will help you to get more accurate thermal conductivity values, but normally we don't know the specific heats of the sample, so you can just ignore it. And so you have two options. One is standard analysis, the other is fine-tune analysis. So as the dialog box says, if you have very low thermal conductivities for the materials, like if you're using polymers or something like with very low conductivities, you can use standard analysis. But in our case, we have a very highly conductive material, so we will use a fine-tune analysis. And again, here, if you are doing a single-sided experiment, you can make this selection, but I won't be discussing single-sided experiment here. So fine-tune analysis. So that's your residual graph. So first, in the calculated graph, you have to make sure that this is a linear curve. But again, we see a lot of bumps here. When you see a lot of bumps, it means that you have to rerun your calculations and make sure it's a smooth straight line. And for the residual curves, there is no specific trend, but again, you should see a uniform distribution of the points In our case, we don't see that. The other important thing where you see all the results on this window, you have measured thermal conductivity, you have measured thermal diffusions, you have the estimated probing depth. The important thing is temperature increase, total to characteristics time, total temperature, time correction, and mean deviation. So you have to make sure that these values are within the safe limits. So right now, if I move my cursor here, it says under low warning level. It means we are in the satisfactory regions. To get the satisfactory ranges for these parameters, you can refer to the manual what are the desired ranges. But one thing you have to make sure that you don't see any red bar here. Red bars mean you are going above the safety limits and you have to lower down your measurement time and heating power. Again, this is an iterative run, so you have to carefully choose what should be the right measurement time and right heating power to get all of these parameters in the safety limits.
How to create this stuff?
So on the numeric results, you can see the system says that your probing depth is 0.5, around 0.5 millimeters. But we know that our probing depth was around 7 millimeters. Nothing is wrong here, but you have to make sure that the probing depth gets somewhat closer to the actual probing depth. This is to make sure that the heat spread you are getting in your sample is almost big enough so that you get the right measurements. Currently, it says the temperature increase is 0.02 kelvins. It means that we are not heating up the sample enough. And also total to characteristics time is very low. It means we are not heating up the sample for a considerable amount of time. So from here you can estimate that, okay, I will need to increase the heating power, so I will get more temperature rise. But at the same time, if you are using more heating power, that means that your total to characteristic time will also increase. So you have to find a very good balance between these two values. So in order to do another one, you will just simply go here, copy, and it will create another column. Just double click on it, and here you can adjust your heating power and measurement time again. So looking at the previous run, we need more temperature rise because we have this temperature rise below the desirable ranges. So let's say if I make the heating power 200 milliwatts, and I can change my time to 20 seconds. So I just double the measurement time and double the heating power. And if I press OK, then I can run my measurement again by clicking on start. But you have to make sure that once you do first run or any run, you have to remove the insulation cover and let the sample go to the room temperature you have, so you don't get any effects of the previous run into your measurement. So as a rule of thumb, you are required to wait 50 to 20 minutes before the next run. So we will do another run after 15 minutes. After you are done with your measurements, you have to remove the sensor. So make sure you pull the sensor very gently towards you, so you don't have to apply any rotation, just a one direction force towards you, and just pull it out like this. So no rotation, just one direction force. Once you are done, you have to put the sensor in the protective casing and put it back in this box.